Hello Math 1K03. This is a video on optimization. So the idea for this video is I'm going to go over two classic examples of optimization problems that one usually sees in a first-year calculus course. The first one is given by the following. So it says a land developer wants to buy a 5,000 square meter rectangular plot of land along a river so that they may build a waterfront restaurant. The land is to be fenced off on the three sides not adjacent to the river. What is the least amount of fencing required for this job? So with any optimization problem, you want a picture. So I've already made this really basic plot here, or basic sketch, sorry, of the scenario that we're in. So the idea is that you've got this river and somebody wants to buy a rectangular plot of land next to the river and they want to fence it. And they want to be able to figure out what kind of plot they should buy in order to minimize the cost of fencing, or minimize, well, essentially that's what that is, right? They want to buy the least amount of fencing possible. So we need a few things, right? So what do we need? The very first thing, we need some variables. So what I would say is the first thing is we're going to let x be the length of the fence. And we're going to let y be the width. Okay, so when we look at this, what we see, so we're going to call, say, this side here the length, and then these two sides the width. I could have chosen the length to be where the y's are and the width to be where the x is. It really doesn't matter here. The only thing that does matter is that we know that we are in a rectangular plot. So we know that the two side lengths there that are perpendicular or form a right angle to the river both have the same length. Okay, so that's the main thing. Okay, so we've got these two variables. We've got the length and the width, and what we're trying to do is we're trying to figure out what's the smallest amount of x and y we need to satisfy all of the conditions that we have here. And the condition is that we need that the area of this plot to be 5,000 square meters. So there's two pieces of information, right? So the first thing, so we know that the area of the plot, right? So it's the length times the width. Oops. Right, it's the length times the width. So if you look at the plot, so length is x and width is y. So the area is length times width. Okay. And we're told that the area has to be 5,000 square meters. So we're told that the area must be 5,000 square meters, right? So what does that tell us? That tells us that we've got the area is equal to x times y, and that must be equal to 5,000. Okay? So we have an equation that represents the area. So the real question, though, right, is what's the minimal perimeter of the fence that we need? Right? Because we want the smallest amount of fencing. So we want to minimize the perimeter. Right, we want to minimize the perimeter of the fence. So the perimeter is just given by the lengths of the sides, right? So we've got a side length of y, a side length of x, and another side length of y. Because remember, there's no... So the thing is here is that this here is not fence, right? So this is not fence here. Not fenced in. Because we only want 3 sides, right? We want a nice open face for the river without fence. So there's only 3 pieces to the fence. So the perimeter is just the sum of the lengths of each of the sides, right? So the one side, so we've got the length is x, and then we've got one side that's of length y, and another side that's of length y. And then to simplify that a little bit, that's just x plus 2y. Okay, so that is our formula for perimeter. And really, this is the function that we want to minimize, right? Because that's exactly what we want to find. The only thing is, though, is that we've got 2 unknowns. We've got the length, and we've got the width. And we don't know how to minimize this thing with 2 variables. We have to only have 1. So a way around this is to use the formula that you've already have. So in other words, right? So if you're given 2 pieces of information, you need at least 2 equations involving the 2 variables that you have in order to solve. So notice that so we can't minimize. Can't minimize this with 2 variables. Okay, so we need to get rid of one of them. Okay, so we can either get rid of the x or we can get rid of the y. It's the same sort of deal that what we did with the box problem in class. So what we're going to do is we're going to use the area condition that we have. So we use the area condition. All right, we're excited about it. Use the area condition. So we know that the area, right, is equal to x times y, which we know for sure is equal to 5,000 square meters. So if we just isolate for y, right, so if we just isolate for y, we end up getting y equals 5,000 divided by x. Okay, and we can actually plug this equation, so plug in this function of x for y inside the perimeter formula that we have. Okay, so we're going to plug this into, oops, sorry, writing's getting terrible here, sorry about that. So we're going to plug this into the equation for p. Because remember, we can't do any calculus or minimizing here with a function that has 2 variables in it. We can only do it with 1. Okay, so we've got the perimeter formula we said was x plus 2y. Okay, so if we're gonna plug this thing into our equation. I'm gonna plug in there. Okay, so when we do that, we end up getting x plus 2 times, and then for y, we have that's 5,000 over x. And we've gotten rid of the y now. So just simplifying this just a tiny little bit, this is x plus 2 times 5,000 is 10,000, all divided by x. Okay, so x plus 10,000 over x is our perimeter function. Okay, so now we've got this perimeter function all in terms of x, right? So just in terms of the length. And we want to minimize this function, right? So to find the min, we need some critical numbers. We need to find the critical numbers. Right, so we need to find the critical numbers. So what that means is that we have to take the derivative of p, and we have to figure out where is the derivative 0, and where does the derivative not exist, because those are where, so the x values for which the derivative is 0, and the x values for which the derivative does not exist, right? That's what it means to be a critical number. So before we take the derivative here, right, so one thing that I'm going to mention is going to be a little bit easier to think of p, so I'm just going to rewrite it here. So p is 10,000 over x plus x there. We're going to use our exponent laws, and we're going to rewrite this as x plus 10,000 times x to the minus 1. Okay, so remember, if you got something in the denominator, if you have to the power -1, you can throw it in the numerator, right? So we've got this thing, and now this is a lot easier to take the derivative of. So p prime, so we take the derivative of x, which is just 1, and then we use the power rule, right? So we've got 10,000, the -1 comes down, x, and then you subtract 1 from the top. And then we've got 1 now minus 10,000 divided by x squared. And just to simplify this a little tiny bit, what we're going to do is we're gonna make a common denominator. Okay, so to simplify, it'll be apparent why we're doing this in a second. So to simplify a bit, we are going to find a common denominator. Find a common denominator. Remember, we want to find where is this derivative 0 and where does this derivative not exist. It's not super apparent. Well, I guess it is kind of it is apparent, I guess, of where it's 0 and where it doesn't exist. But there's an easier way to see it written in a different form. So what we're going to do, so we've got p prime equals 1 minus 10,000 divided by x squared, and then we're going to make that 1 an x squared divided by x squared. So now we can safely subtract the 2, right? So now this is equal to x squared minus 10,000 all divided by x squared. Okay, so now that we have the derivative in this form, it's a little bit easier to see. So remember, a derivative does not exist where it doesn't make sense to plug in certain numbers, right? So by looking at this fraction, what's a number that you can't plug into it, right? So if you think a little bit, if you look at the denominator, we can't plug x in or we can't plug 0 in for x, right? Because that way we'd be dividing by 0, and that's not good, right? So we have p prime does not exist when, or at x equals 0. Okay, so the derivative does not exist at x equals 0, so that is a critical number. And another critical number is where p prime is 0. So p prime is 0 when the numerator is 0. So remember, if you have a fraction and you've got variables in the numerator and the denominator, if you set that fraction equal to 0, it doesn't matter what the denominator is, right? There's nothing you can stick into the denominator that's going to make it 0. It only depends on the numerator and where it's 0, right? So in this case, our numerator here, right, is x squared minus 10,000, right? So we only care about when that's 0. So p prime is 0 when x squared minus 10,000 equals 0. And so just rearranging a little bit, what we have, so x squared equals 10,000, so just bringing the negative 10,000 to the other side. Then we can take the square root of both sides, right? So now we're looking at plus or minus the square root of 10,000, and then we have x is plus or minus 100, right? So the square root of 10,000 is 100. So we have three critical numbers, right? So we have three critical numbers. Right, the first one that we found was x equals 0. There's the other one that we found was x equals minus 100, and then there's another one that was x equals 100. Okay, so remember when we were talking about in class, this is a real world problem, right? So we have to think about which of these numbers make sense and which of them don't. So if we go all the way back up to our picture, right? Oh, pretty far up. Okay, so we go all the way back up to our picture, and there's our x. So if I get rid of that and that, so our x is the circled variable here. Remember our critical points were 0, negative 100, and positive 100. Does it make sense for the length of a rectangular fence to be negative? No, right? Likewise, does it make sense for the length of this rectangular fence to be 0? No, right? So if you go all the way back down to where we were, right, so our critical numbers were 0, negative 100, and 100. So the first thing right off the bat, we know that x equals minus 100 does not make sense. In terms of just mathematically, it makes sense. But in the physical sense, in terms of our problem, it doesn't, right? So x equals 0 and x equals negative 100, they are critical numbers, but they don't make sense for the physical context of what we're looking at. So we have x equals negative 100 does not make sense since we can't have negative fence length. Okay. In the same way, x equals 0 also doesn't make sense. Since if x equals 0, we would have no length. Okay. So therefore, x equals 100 is the only one. The only one that makes sense. Okay, so x equals 100 is the only critical number that really makes sense in our context. And so we have to think back to what we were doing, right? So we're trying to minimize the perimeter function. So what we really need to know, does x equal 100, does that correspond to a minimum, right? Or does it correspond to a maximum? Or is it nothing, right? So how do we figure this out? So, well, how did we figure out any other time whether a critical number corresponded to a maximum or a minimum? Right? We use the second derivative test, right? So how do we know x equals 100 corresponds? Oops. How do we know that x equals 100 corresponds to a min? Okay, so we'll use the second derivative test. It's really important that we check that this corresponds to a minimum, because if it corresponds to a maximum, we're doing the complete wrong thing, right? So we have to make sure that it really is a minimum that we're getting here. So for the second derivative test, you need the second derivative. So let's do that. So we had p prime is equal to 1 minus 10,000 divided by x squared. And then we can rewrite that, kind of like last time, as 1 minus 10,000 x to the negative 2. So the second derivative, so the derivative of 1 is 0. And then we can use the power rule. So we got minus 10,000, negative 2 comes down, x to the negative 3, so we're subtracting 1 from the negative 2. And then another way of saying this, so we got the negative 2 times the negative 10,000 is positive 20,000. And then we're dividing by x cubed, right? Because that's x to the minus 3. Okay, so we've got that. So we stick in our critical number, which is 100. So p double prime at 100. So that's going to be 20,000 divided by 100 cubed. They're both positive numbers, so the fraction is going to be a positive number. And remember, if the second derivative is positive at a critical number, that tells you that it corresponds to a min, right? So x equals 100 corresponds to a min. By the second derivative test. Okay, so now that we know that x equals 100 corresponds to a minimum, we have to stick that number back into the original function to get the minimum perimeter, right? So all we need now is to plug x equals 100 back into the original function. P. Okay, so doing that, so remember P is x plus 10,000 divided by x. So if we plug in 100, so P at 100 is 100 plus 10,000 divided by 100, which is 100 plus 100, which equals 200, right? So therefore, the minimum amount of fence would be, the minimum amount of fence needed would be 200 meters. For this last question, we're going to look at this neat little problem called the maximized product problem. And what it's asking you to do is to find two positive numbers such that their sum is equal to 100 and their product is maximized. So there's a bunch of different numbers that add up to give you 100 that are positive, right? So like, say, 100 plus 0 is equal to 100, or 99 plus 1, or 98 plus 2, and you can keep going and going. And so the question is, what are the two positive numbers that you can add together such that when you multiply them together, it gives you the biggest number out of all of them? So the way that we do this is, first we need a function that we want to maximize, right? So first we're going to say, well, the sum, so we'll let x and y be two positive numbers such that x plus y is equal to 100, right? So their sum is equal to 100. So we'll call the function s. So we'll say s is equal to x plus y. Okay, so we want to maximize, so actually no, sorry, so this is the sum, right? So the sum is x plus y. What we want to maximize is the product, right? So we want to maximize we're going to maximize the product p, which is x times y, right? So just like the last problem, we can't maximize this thing with having two variables in it, right? That's the big problem with these optimization problems. There's always one too many variables floating around. So the big issue, right, is you can't maximize with two variables. Okay, so we need to make a function using the information that we have in order to get rid of either the x variable or the y variable in the function p. So what do we have? Well, we know that x plus y equals 100, right? So we have x plus y is equal to 100. So if I just isolate for y, right? So we have y is equal to 100 minus x, right? And we can plug that in to the product formula, right? So we can plug this in into p equals x times y, right? So p equals x times y. This is the same thing as x times 100 minus x, because 100 minus x is the same thing as y, right? Just by the formula that we have. So we've got that. So then we'll multiply through the x, and then we've got 100x minus x squared. So that's our function for the product, right? So the next thing that we want to do, right? So we want to maximize this thing. So we want to find some critical numbers. And again, what critical numbers are, they're the x values such that the derivative does not exist, or x values where the derivative is 0. So the thing is that this is a really nice polynomial, and the derivative is going to be nice, right? So you've got p prime is equal to 100 minus 2x, just using the power rule, right? So if you've got p prime is 100 minus 2x, well, this is a really nice function, and it exists everywhere, right? So p prime always exists. Right, so the only other critical numbers that we have to worry about are when p prime is equal to 0, right? So p prime always exists, so where does p prime equal 0? Okay, so well, that happens when 100 minus 2x is equal to 0, right? Or in other words, when 2x is equal to 100, or then just dividing by 2, that's when x is equal to 100 divided by 2, which is 50, right? So that's one number that we need, right? So x has to be equal to 50, right? So what? So x equals 50. Now, how do we know that this is going to correspond to a maximum product as opposed to a minimum product, right? So again, we can use the second derivative test to check this out. I'll let you take care of that. Just note that take the second derivative here, and you'll notice that it's always negative. So just as a little bit of work for you to do, it might be good preparation for the exam. Just show to yourself that x equals 50 does actually correspond to where a maximum occurs using the second derivative test. Okay, so just for now, you can take my word for it that x equals 50 does correspond to where a maximum is. And so we need the two numbers though, right? So we have one number, x equals 50. So what should y be, right? So what
should y be? Right? So we'll use the formula we made. Use the formula we made. Right? So the formula that we have at the top was y was equal to 100 minus x. Well, if x equals 50, this tells us that y is equal to 100 minus 50, which is equal to 50. Right? So x equals 50 and y equals 50. Okay? So those are the two numbers. So then you check, obviously, so 50 plus 50 equals 100. And out of all positive numbers possible that add up to give you 100, 50 times 50 is the largest product that you could possibly get. Okay, so those are two classic optimization problems that you would see. So yeah, try to absorb the idea of how these things work. And yeah, so hope you enjoyed the video.